Guys, what's happening? This is the second video in the magnetic field math section. So I wanted to work out a couple of problems with you guys based on our magnetic field at a distance. So here is what we said. Okay. Okay. So we said that the magnetic field is equivalent to our permeability of free space times the current over 2 pi r. Okay, so let's see. I've got, we got to realize that our permittivity of free space is this here, and we know that that equals 4 pi times 10 to the negative 7th Tesla meters over amps. Okay, so let's figure this out. I've got a question for you, and the question's a simple one. It says, what is the magnetic field at a point 0.5 meters away? So the radius is 0.5 meters from a wire carrying a current of 40 amps. Okay, quite a current in that wire. So what is the magnetic field, okay, of a current carrying wire at a distance of 0.5 meters away? So in picture form, that might look like this. Okay, we know that with the thumbs up, the current is kind of going around this way. Okay, so we're looking at how strong the magnetic field is at a distance of 0.5 meters. Because as you get further away, we know the field decreases. So let's just see. So if I'm at a point here, I should be able to measure the magnetic field of a wire that a wire produces. So let's take a look at it. B is 4 pi to the negative 7th times 10 to the negative 7th times the amperage, 40 amps, over 2 pi, and then times 0.5. Okay, so I will, let's do the math out here. Okay, I'll do it out and then get an answer for you. Okay, so what I've done is I've done 4 pi is 4 pi times 10 to the negative 7th times 40 over pi. Well, 2 pi times 0.5 is just going to be pi. So after doing the math here, 12.6 to the negative 7th times 40 equals that divided by pi. Okay, I got a B field of 1.6 times 10 to the negative 5 Tesla. So I got 1.6 times 10 to the negative 5 Tesla. And you can, as you can imagine, we could ask you a bunch of questions. We could ask you, we'll never ask you what this is. Okay, this is a constant. I might ask you what the current is given a distance and a magnetic field. I might ask you what the distance is away given a magnetic field and a current. Okay? Leave that up for a few seconds for you. Okay, here's our last section here. We saved the hardest for last, I suppose. So here's the situation. We're looking at what the force is between two wires carrying a current. So if I have a wire, we'll call this wire A and call this wire B. both of them, okay, are going to be carrying a current. So, and we want to know what kind of force exists between the two wires. Actual force. So I actually took two wires, wire 1 and wire 2. There'd be a force between the two wires that could be felt, actually. Okay, so the D represents a distance between the wires, and we realize that if we hold our thumb up, this is the direction of the magnetic field, our B field, and we are going to be taking a look at how to calculate the force between wire A and B. And according to Newton's third law, we also know that equals the force of B on A. So the force felt on each one is going to be the same on each other. So we end up saying that all this, the force, now get ready for this, is equivalent to our permittivity of free space multiplied by the current in A multiplied by the current in B over 2 pi d multiplied by the lengths of the wire. Okay, so we already know what these terms mean. It's just a matter of getting it into the formula here. So the force felt from this wire to this wire would be equivalent to our permittivity of free space times the current of the first one times the current of the second one divided by 2 pi d, all multiplied by the length of the wire. Again, just an algebra problem, and I'll give you one question to look at to try to solve. One more thing I failed to point out was that if these wires are going in the same direction, they're going to repel each other. So because they're traveling in the same direction, the magnetic fields push away from each other. So I'll write a little side note here. Okay, that way you can get that in there. So parallel, here's a side note. In the same direction, okay, attract. Okay, parallel in the different direction, repel. Okay, I know just a second ago I said that that they going in the same direction, they repel. I'm not going to make another video based on that mistake. Okay, so I'll just erase these here. Okay, and we are going to say that if they're going in the same direction, they attract each other. If they're going in different directions, they repel each other. Okay? Okay, I'm going to try to do this question in 1 minute. Okay, here's the question. What is the magnitude and direction of the magnetic force between two parallel wires? They're both 5 meters long. Their distance is 2 centimeters apart. And each one carries a current, I1 or A, IB would be 15 amps. Okay, so let's see if I can get this done. I don't think it's going to take less than a minute. Sorry about that. Okay, so we said that the force of A on B. Okay, have these. So we got two wires here. We got wire. Okay, they're going in the same direction, so they're going to attract each other. We know that F A on B is equivalent to permittivity of free space times current 1, or A, times current B over 2 pi D times L. I know that's a lot. I'll solve it right now. Okay, now I know I had just a time lapse there for you. But what I did was I just plugged in some numbers, and permittivity of free space times both currents divided by 2 pi over the distance. Now I had to change that from centimeters to meters, just so you know. So 2 centimeters is 2 times 10 to the negative second meters. All right, and then I multiplied all that by 5 meters for the length of the wire. So what I got for an answer is, I don't know if you can see that on the screen. I got 0.011 newtons, and they attract each other, okay, because they have the same direction. Okay, so again, just an algebra problem, really. And if you can manipulate variables, you'll be able to solve for. You can solve for current, you can solve for current, you can solve for the distance, or even the length. Okay, so you'll see a bunch of problems like that. I think that'll be it for this video. A bit long-winded.